Hello everyone, and welcome again to another stream here on Freaky Physics, and we will have another lesson today. I sound a bit off. Yes, I have a cold. Well, I think it's a cold. Uh, it's just a head cold here. So today we're gonna have Gita again. We're gonna do. Oops, I forgot to update the titles. Let's update that now. What exactly are we doing today? It's a mix of physics questions, different topics. So that's what I'll put here. So I'll just say physics for IB. All right, let's just update that. Yeah. So yeah, apologies right now in advance for doing this. It is a bit annoying, but I can manage, so no worries. We will start in about a minute, and we'll just get right into it. Let's join the classroom. And okay. Okay, it's taking a while. Okay, we're buffering a bit right now. The internet's not that strong. The connection's not that great. Okay, there we go. I hope that's better. Okay, if I recall right, maybe not the last stream. The stream before that got broken up into two parts because of the internet stability. Yeah, let's just hope that right now it is gonna be more stable. I'm trying to join in. Ah, yes. Oh, by the way, how do I sound this time around? Let me know if it's a bit louder or clearer or more muddled. Yeah, you tell me. Okay. Huh. Okay. Let's go do this. Let's try that again. Let's join the lesson now. Uh-huh. Well, it's taking a while to connect. Alright, I do have my phone here ready to use as a hotspot in case stuff goes wrong in my side. But I'll just get it ready. Oh, it's already here. What am I using right now? Oh, okay. I think that's the reason. I better connect to the other one. Okay. Reconnection successful. Let's see. All right. I'm back, I hope. And now let's see if I can connect properly. I'm already late for 2 minutes. I just realized I was connected using my mobile hotspot, so that's why the internet was a bit unstable there. All right, classroom's loading, and okay, there we go. There we go, and we're joining the classroom now. All right. Hello, Gita. Good afternoon. How's everything?
Great.
Yeah.
How about you?
Well, aside from having this blocked nose, I'm okay.
Oh. Also, as everyone's sick in our family.
Yeah, I think I also got this from one of my students. There was because normally when I go to school, I normally wear a mask, even though COVID's finished, right? I still wear a mask because I found that whenever I took off a mask, I'd get sick from one of the kids, from one of the other students. So it happened last week. I didn't wear a mask last week at all, and yeah, this happened. All right. Share that. And let's also do this. Go to the board. Okay. Okay, let's do it like that. All right. So, okay, let's start. So the first one the first question we want to go through is this. Okay. So there's wait, sorry, that's the second part of it. There's another one, right?
Yeah, I think there's 2 parts before that.
Yeah. I think this is where it starts. So let's do this first. Okay, so in this case you have the diagram of an AC generator with a rectangular coil rotating constant frequency and a uniform electric field like so. Right? And okay. Where's question A? Hold on. Okay, that's 3. That's B.
Possible that I skipped A.
All right, I think you skipped A. So let's go straight to B. Okay, copy this image. Okay, let's just delete that and do that again later. All right, so all right, here we go. So that's the generator output of the voltage as it varies with time, right? Okay, electrical power is produced by the generator. It's delivered to a consumer some distance away. So the average power output is given here. So we have to calculate the root mean square value of the generator output current. Okay. Okay, in order for us to do this, the average power, the formula here is average power is equal to, well, let's remove the word average for now. In electrical circuits, right? In electrical circuits, what we have is the power output of any source would be equal to the current it outputs times its voltage, or the potential difference that it has. Okay. Now, in DC circuits, this is perfectly fine. Perfectly fine, right? But the problem is we don't have a DC circuit. We have an AC generator. So we have to kind of modify this a bit. But it doesn't really take much to modify it. We're just going to put average here for power. This is going to be the RMS here. And this is going to be the RMS here. Okay. The reason why we do this is because RMS is basically a measure of an average.
Yeah.
Okay. So basically what we're doing here is we're doing average power equals average current times average voltage, right? And thing is, we do know how to calculate RMS knowing something here. We see here that the peak voltage, so V peak, is equal to 25 kilovolts, right?
Yeah.
Okay, so the RMS here, the idea here is, what's the relationship between RMS and peak? So V RMS, there's a relationship. It's gonna be equal to something times V peak. That's going to be square root of 2 over 2. Okay.
Wait, sorry, I don't understand.
Okay, let's take a look at why this is the formula. Okay. RMS. Okay, let me just look for an image here. Okay. RMS voltage. Yep. Okay. Yeah. Now, the reason for that, I think it's gonna be easier if I do this here. Now, this works because this, let's do this in math first. This is a sine function, right? You can see that the wave looks like a sine function. Or it could be cosine. So, sine or cosine, right? Okay. Now, the idea here is to find the average, because the idea here is, I think I better look for a wider image for now. Hold on. So it's easier for us to do. Okay. Okay. I think this is gonna work. Hold on, copy this image and let's move to the side. Okay. Okay, so here is another sinusoidal voltage wave, right? Now, here, this is the peak voltage from here to here, right? And then this is peak to peak. And you see here that the average voltage is up to there. Or this should be properly, and let's zoom in a bit. That's properly RMS, okay? Okay, because if you think about it, what's the actual average voltage? The average voltage actually here is 0, strictly speaking. Why?
Yeah.
Right? Because this and this cancel out, so to speak, right? But in terms of a circuit, it doesn't really care which way the current flows. What matters in a circuit is that current flows. And therefore, in a circuit, it doesn't matter what the direction of the potential difference is. It matters that there's a potential difference. So this is not useful. Not useful idea. Okay? So in order for us to get a more useful idea, let's go to the term RMS. Okay? You recall what this means. What does
Root mean square.
Root mean square. Okay? Now, we do RMS in this case because of the negative values. Why? Because if we take the RMS is you take the square first, square the values, then take the mean. Okay? Then, so this is gonna be first, the second step, and the third step is take the square root, right? Square root. Okay, so that's the whole idea, but let's take a look at what happens if we actually do that here. Let's lock this. Let's erase everything else for now. Here. Okay, so basically, if we square this part of the wave, we get this. Right? So this is the square part. Right? And then if we square this, we get the same thing. We square this, we get the same thing. And we square this, we get the same thing. Something like that. Right? So what happens here when you take the mean? So the mean here would be somewhere here, right? I'm going to change the color first. So the mean here is going to be somewhere here.
And
this is the mean of
have to
squares.
take the...
Yeah, exactly.
Right.
Yeah, exactly that. We have to take the square root of that. So this goes down here. This is the RMS already. Okay. So the reason we do this again is because it's more useful as an idea in terms of actually putting it in a circuit. This tells us that we can get power out of AC, even though it's moving back and forth. Okay. All right.
We just take the mean of the top values.
Yes, so just the black ones here, the black square values. Okay, we don't take all of them. Of course, that's going to be difficult if you do it one by one, but of course, there's a method to do it mathematically. For now, we'll just say that this mean here, so let's say this is VP, right? The peak. Okay, this is going to be the VP squared, right? So this right here is going to be 1/2 of VP squared. Okay.
Yeah.
So because of that, and then if we take the square root, so the RMS would be equal to the square root of VP squared over 2, which is the same as saying VP square root of 1/2, the same as saying VP times over root 2, which is the same as saying, again, VP root 2 over 2. Okay, so any of these forms would work. But the easiest way for you to remember that is that this mean of squares is going to be half of the peak voltage. Okay?
Okay.
All right.
Yeah.
All right, so now that we've established that, let's go back here. So what are we going to do? We're just going to solve for the RMS voltage here. This is just going to be, let's do it the easier way. In physics, we can just say 1 over root 2, right? We don't have to express this in root 2 over 2. So this is going to be 25 kilovolts divided by square root of 2. And that, calculator, okay, 25 divided by square root of 2 gives us that. So this is going to give us 7. Let's use 18 kilovolts. Okay. All right.
So we always multiply it by root 2 over 2.
If for most of the problems that we do with RMS, yes. Okay. Will there be exceptions? Yes, there are exceptions. But in DP, no. There are no exceptions. We have to use this. Okay.
Okay.
All right.
So we just always do this. We
Yes.
never have to calculate ourselves.
No need. Just go straight to this formula. All right.
Okay.
Okay. So going back. So now that we've solved for the value of the RMS voltage, we now just have to put that here and find IRMS. Okay, that's gonna be equal to the average power over VRMS, right? And we have our values. The output power is 8.5 times 10 to the 5 watts divided by the VRMS of 18 times 10 to the 3, or 1.8 times 10 to the 4 volts. That's gonna give us how many? Okay, so let's do that. 8.5 exponent 5 divided by 1.8 exponent 4. Okay, that's gonna give us 47 amps. V equals IRMS. Okay. 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 Formula wise, it's pretty straightforward, but I think the problem here was really what's exactly happening, right?
Yeah.
Okay.
And I didn't know the formula actually.
Oh, you didn't.
I mean, I didn't remember it.
Okay. I'm curious. Is it in the data booklet? It should be, but let me double check. So this one's done. This one's done. Okay, let's do this. This is the next one. All right. This should be in topic. It's either topic B or let's see. Thermodynamics. Topic 3. Oh, it's not in topic 3 for some reason. Is it in topic 4? No, it's not.
Yeah.
No, it's not. It's not. It's in neither topic. So that's why you didn't learn it. Okay. But okay, either way, let's just go through the next question. Part 2 you didn't put up, right? We are going straight to part 3.
Yes.
Okay.
Yeah.
All right, so let's put this on part 3. Okay, here we go. So the frequency of the generator is doubled with no other changes being made. Draw on the axes the variation with time of the voltage output of the generator. Okay, I'm going to draw it now, and I believe you're gonna have questions once I draw it. Okay, but I will just do it first. Okay, where is the question? Here. Okay, I'll just copy this. Oh, I cannot. Okay, I'll just erase everything here now. Right here. Yeah, we'll keep that part though. We will draw this. The frequency doubles, so the period will be half. So in other words, the period right now is 10 milliseconds. So we're gonna have, I'm gonna draw a partial one first. Actually, no. Double means double. It should be 10, 5. Okay, there. Something like this. That should be at 15.
How do we know how to draw it?
Okay, so first of all, let's do it here. Let's put it at the bottom. Okay, it says here the frequency doubles, right?
Yeah.
So this means the period is cut in two.
According to what formula?
Well, the relationship between period is equal to 1 over frequency. Oops, sorry, period should be t, right? This is the relationship between the period and the frequency. So if f becomes 2f, then t becomes half t. Okay?
Yeah.
Okay. So that's the first part. The second part here is, and this part is not so obvious, but this one is, right? The second part here is, if it's cut in two, then that means the rate of change in well, let's just put it in the formula. It's gonna be easier. Okay, so remember that the EMF, the induced EMF, that's gonna be equal to negative n, then change in the magnetic flux density over the change in the time, right? So
Yeah.
if we assume that these are constant, right, then what happens here? This is halved, right? Okay,
Yeah.
because that's constant and the time is halved, what happens to the EMF? So the EMF induced is doubled.
Oh. Yeah.
So this is you put these together, so you put that fact that the frequency doubles, it's gonna have a double effect. It's gonna change the period and it's also gonna double the EMF. That's why back on the graph, it's double the peak and twice the frequency, or half the period.
Okay.
Okay. All right. Is that clear?
Just can we go back to the graph?
Okay, go ahead. Let's zoom into it.
So, but shouldn't? Oh, I understand.
Okay.
So there's two.
Yeah, because compared to this, there's like one full wave here or one full oscillation here. We should have two full oscillations here. Actually, now that I think about it, this is 4 full oscillations. This is wrong. Sorry. There should only be 2 full oscillations. My bad. Okay, so this is peak here at 5. The peak here should be at 2.5. Should be here. Then 5. Okay. All right. I see what I did wrong. Okay. So full wave. So this is gonna be, so up to 5. So up to 10. Then up to 15. Then up to 20. Something like that. All right. So this is the better one. Okay. All right. Only twice as much. All right. Is there anything you'd like to ask you?
I understand.
Okay, great. So let's move on to the next question that you have. All right. Let's see. 10, question 10, question 10. Okay, let's do the quantum mechanics question that you have here. All right, so here you have an electron beam. It's used to study the nuclear radiation of carbon-12. Nuclear radius rather. The beam is directed from the left at the thin sample of carbon-12. Detector is placed as an angle here, and relative to the direction of incident path. The graph shows the variation here. There's a minimum of intensity here at I equals I0, right? Okay, yeah. So let's take a look at the actual question. So now that we know what the setup is.
But I don't really understand the graph.
Okay.
The experiment.
All right, in that case, let's do the graph first before we do the questions, okay? Hold on, I'll just paste the questions here. What does this graph mean? Okay, first of all, basically, it's just telling us that for every angle, there's a certain intensity of electrons. Okay, so this means, let's go back here on top. If theta is 0, if the detector was here, that's gonna be it. Okay, that's the intensity. So you can see that this is a maximum, right? So if you move the detector here, that's gonna change the angle like that. So what's happening here? From this value to this value, so as theta increases, intensity, so electron intensity decreases, right? In other words, there are fewer and fewer electrons getting into the detector. Electron intensity decreases. Okay. Now, the problem here is you would expect this to just keep going like that. That's the expectation, right? Because it kind of makes sense that because of the detection, because of the fact that those electrons will be deflected, you expect something like this graph. But you see here, this is the weird bit. This is weird. This is strange. Why? Because there's a sudden spike. Right? Okay.
Yeah.
All right. Now, what's that spike about? Okay. So what's gonna happen here is the electrons, yes, they're being deflected, and most of them are not being deflected. And then the more deflections you have, the fewer electrons you also have, right? But okay. Okay. But here's the problem. Let's kind of look into the idea first, okay? Let's say that this is your carbon atom and this is your carbon atom, right? Okay, and let's say that you have several electrons going in like this, okay? Let's just say that they're all moving straight like so, right? So think about it. This one thing is being pulled equally in both directions by the two carbon atoms, so it's gonna go straight through, right?
Yeah.
This particular atom here, this is kind of like experiencing a bigger force, so it gets deflected like that, right? So I'm just gonna go to this particular thing and say that this is your theta 0, okay? That's your minimum. Similarly here, this would be experiencing that and that force. So these will be the forces, and therefore it's gonna go like that. So it's also gonna be, this angle will still be theta 0, right? Okay. Now, what's gonna happen with these two electrons? Let's just pretend that there's no collision for now. Let's just pretend that it's just gonna pass through, but something happens. Okay. Now, with this case, it gets close enough, and look at that distance here, and in here the distance is close to the what's this? The distance between the electron and the carbon atom is close to the de Broglie wavelength. I don't actually know how to pronounce this properly. I just heard it from one of my professors from before. Okay, wavelength. Okay. Okay, the distance here is close to the de Broglie wavelength. So in other words, here, these electrons here act like particles, right? Okay, but this electron here acts like a wave. Okay, so particles, but this electron here acts as a wave because of the fact that the distance between it and that carbon atom is close to the de Broglie wavelength. Okay. Alright.
Well, how can we know that if the detector doesn't detect it?
Sorry, say that again, please.
How can we know that if the detector doesn't detect it?
Well, the idea here is, let's just go back there first. The detector is not actually just one piece of equipment like this. This is a simplified version of the detector, right? A real detector in these kinds of experiments would actually be more like this. So you have this, and then you have several detectors in this thing. Okay, so this is the detector, and each one of this is a sensor.
Okay.
Okay, all right, that's how we do it in modern physics, but of course back then, back in the day, it's really a single piece of something. Okay, all right, so going back, go ahead.
But it can only take in so much information if it's like small.
Yeah, that's right. So
So what would it tell us? It would just tell us how many electrons pass through.
yeah, it's telling us how many electrons have hit the detector, whether it's the single piece here or the big array here. Okay, each of these sensors would tell us how many electrons it has counted. It's literally counting electrons. Okay,
But even if they get deflected or if they go straight, they're still going to be the same amount.
yeah, okay.
Or is there going to be less?
So this is going to be where the graph comes in. So if we do this, basically these electrons will detect a large number of electrons. Okay, now these ones here, fewer. This is also fewer.
Why?
Okay, what's the easiest way to do that? Actually, this is where this comes back in. Now if you look at this, doesn't this look familiar? This looks like, okay, if you think of the electrons as waves now, okay, so in this case we will ignore those matter particles first, or those matter electrons, right? We will now look into, I shouldn't erase that, I'll just make a new one. Okay, let's look into the wave electrons, so to speak. Yeah, okay, so we will ignore the matter electrons and just go straight to the wave electrons. There's your carbon, and there's your carbon, and then we're gonna just do the matter, the wave electrons, right? So this, let's just do a couple of electrons here. Okay, so each of these electrons is producing a wave, so to speak, right? So basically, because that's a wave, it's gonna go here, and then it's gonna do this. What is this? You've learned this before, right?
Yeah.
What is this? What's this phenomenon called? This is diffraction.
Diffraction.
Right? And the thing about diffraction, it doesn't just spread, it actually produces an interference pattern. There's gonna be a maximum here, right? I'm using the wrong color. Let's just do that here. Let's use red. Okay, orange. Okay, so what's gonna happen if you put that on a screen of sorts? You're gonna get a maximum here, then another maximum here, then another maximum here, another maximum here, maximum, like that, right? So
yeah,
looking at wave electrons. Okay, so you get a diffraction pattern and you get this, and that's exactly what this graph is showing us. This graph is showing us exactly what to expect. The electron intensity decreases here. So if we go back here, this basically is, let's say this is the central maximum. Actually, no, let's just do it like this. If we put that here, this is the central maximum. So what's gonna happen? It's gonna become less and less intense. It's gonna get, well, it's not gonna become zero exactly. It's gonna do that, and then it's gonna do that again, right? So, and then gonna start dipping off again. So if you continue this, this actually goes into like that, something like that. Okay. All right. So.
Sorry.
Go ahead.
What causes the other peak?
This peak, okay, so this is the central maximum. I'll just write it here. This is the central maximum of diffraction pattern, right?
Oh, and the others is the other peaks.
Yeah.
Max.
So this is the second peak, or the first order peak, first order max. Okay. So this would be the first minimum. Okay, now here's the thing though, before we continue with the questions, let's go back to what we did here. Now Remember, I told you we can just ignore the matter part, the matter electrons, and focus on the wave electrons.
Yeah.
Okay, we actually have to do that because in the actual spacing between carbon atoms or any solid atoms for that matter, your electrons will always have the wave properties. Okay, so okay, so that way we can actually see that diffraction happens in a solid just like that. Okay, and there's gonna be a pattern. Okay, so does that is that a bit clear now?
Yeah, but it's really confusing.
Yes, I know. The reason why this is confusing, in my opinion, is because you have to remember a lot of classical physics, but also at the same time try to forget a lot of classical physics. You don't know which one to remember, which one to forget, right?
Yeah, but in this case, we're looking at the electron both as a particle and a wave. Not really. But
Not really. We're looking at the electron as a wave in this case. Okay, so let's answer this now. Let's discuss how the results provide evidence for matter waves. Okay, so the idea here is, what's the main idea here?
is it because they make a pattern so
Okay,
we can see that
an
they pass
interference pattern, right? An interference pattern is seen, right? With clear, not even a clear, with clear maxima and minima, right? Maxima and minima. So what happens here? That's one mark. You have to now relate that. So this provides, or rather not provides, this means, let's just say this means that the electrons are exhibiting wave-like behavior. Wave-like
But
behavior.
can we say that?
Okay. What do you want?
What a matter wave?
If it exhibits matter-like behavior, then what you're gonna see is, I'll just do it here on this side. Matter-like behavior, pure matter-like behavior. This would be carbon and carbon. These would be your electrons, right? You'll actually see a more or less equal distribution, as you said. You're gonna see a more or less equal distribution of scattering. So equal scattering. Okay. Scattering if purely matter particles. Okay, purely matter particles. Okay. Oh,
Right, and so matter wave is when they split up and some of them act like matter and some of them act like waves.
yeah. But again, once we get to the scale of atoms, we just ignore the matter particles. We just go straight to the wave properties. Okay. Just to give you an idea of how big we have to go into matter, pure particles. Quantum mechanics using what is it? The wave-like properties of matter has been observed up to the molecule scale. It has been observed to the molecule scale. Okay. So imagine this in the atomic scale. It's gonna be all pure wave properties. Okay. All right. Okay, so let's go to the second question. But before that, excuse me. Hold on. All right. All right, number 2. So we have the accepted value of the carbon-12 atom is given here. Estimate the angle theta 0 at which the minimum of the intensity is formed. Okay, so we're gonna look at this from another point of view. Here, we looked at it like the electrons are passing around two carbon atoms, right? We can look at this at it's gonna be exactly the same in terms of the math. But you can look at it like this. This is the carbon atom. And this time around, instead of having to pass through the space between the carbon atoms, the electrons are gonna pass around the carbon like that. Okay, so this is an alternate way of looking at it, and in this case, you can think of this still as having a single slit operation, wherein the slit separation here, this is your slit separation. Okay, and we do have a formula. Okay, sorry, go ahead.
Sorry, how did it pass through the carbon?
Okay, remember that they're waves at this point and not particles. So what's gonna happen here? So these two are obvious; they just pass through, right? And so do these, and so this may also do it. But this one in the middle, if you think of it as a solid particle, then it's really not gonna pass through. But if you think of it as a wave, so let's just think of it as a wave like that. So you see, as a wave, it diffracts around the carbon atom like that. Okay, and then because of that, it passes through. Okay. All right.
Yes.
Okay, so with that in mind, let's actually do the thing. We are, let's go to the data booklet, because again, one of the formulas I haven't memorized. Okay. Let me just see diffraction path, single slit diffraction. Let's go single slit diffraction. Single slit. Okay. We're gonna do this formula. Okay, so S. Okay, S is equal to lambda d over d, big D over small d, right? Our S here is the separation distance of maxima. So that would be the S would be, that's kind of we're looking for that. Okay, we're looking for S, and then lambda would be the wavelength of the particle here, but we need to find that. Okay, so we need to find the de Broglie wavelength of the electron. Okay, and how do we do that? There is also a formula for that, right?
Yeah.
What is it? Let me see. Yeah, H over P. Is it? Yeah, H over P.
It's not in the
H over P. Okay, so that's the thing. So we're gonna put that into the formula. So we're gonna do S is equal to H D over P times small d. Okay, Planck's constant, we have a value for that. We'll just keep it H for now. The D here is the diameter of the carbon-12. Okay, so we're gonna do 4.94 times 10 to the minus 15. And then the D is that gonna work? Okay. Yeah. Hold on. Let me see if we can simplify this. Oh, okay. We need something with an angle. I think there's a better one if we use something with an angle. Hold on. Okay, I think this is better. So let's try. Let's change our formula. But we're still gonna need the wavelength, the de Broglie wavelength of the electron. Okay. Lock. All right. Why is this a better formula? Because there is a formula straight away which uses the angle. Okay. Okay. We're gonna use n lambda equals d sine theta. There we go. That's gonna be better. So from here, what are we gonna get? Since we want theta, so theta will be equal to sine inverse of n lambda over d. Okay, where d is the diameter of the carbon-12 again, and we here would be 1. Okay, so that's gonna be 1 times h over p d. Let's put d here as, let's keep that. What's the value again? 4.94 times 10 to the minus 16 meters. Okay. Now, the problem now is, what's the momentum of the electron? Okay. Is there any information given here? The electron beam, I think it's part of A at this point. Okay, because we need to know how fast the electron is moving. And that's gonna give us the momentum.
Oh, it's possible.
Okay.
I don't know if I wrote it down.
Okay. Now, I'll just put this here while you're searching for it. You can find the momentum can be found from MV, or momentum can be found from the energy, kinetic energy. Okay. EK P squared over 2m. Okay, P squared over 2m. So one of these, you will definitely need the mass either way. But that's an electron. That's in the data booklet, right? So we just need either the energy of the electron or the velocity of the electron. Either one would work. Once we have that, we put that in the P here in the formula here. Okay?
So it said, show that the wavelength is 3 times 10 to the minus 15 meters. And we have the energy is 4.2 times 10 to the 8 EV.
Okay, there we go. 10 to the 8 EV. The wavelength was, again, how many? 3 point something times...
3 times 10 to the minus 15.
Minus 15 meters. All right. Do we need to change? Yeah, we need to change. Go ahead.
Right, and says the de Broglie wavelength lambda of a particle accelerated close to the speed of light is approximately lambda equals hc over e.
Yeah. All right. So we can use all of those and basically put them in here. All right. Okay.
Yeah.
At the moment, I think that's good enough. We just need to solve for. Basically, we just need the momentum. Then from there we find the angle. Okay.
And we used v equals lambda f.
V equals lambda f. No, we don't need that. We don't need that.
How do we find the momentum?
Again, momentum would be straight from energy. Okay, so let's go back here. If you're given the energy, you express this in joules. And then there we go. We put that energy in here, in the second formula here. P squared over 2m equals EK, the kinetic energy.
Okay.
Okay.
Yeah.
Right. Let's take a look at the question here. Outline why electrons with energy of approximately 10 to the 7 electron volts would be unsuitable. It doesn't have enough energy to... So in this case, what happens? If your energy is lower than the energy we have here, right? Will it actually... Does it have the correct de Broglie wavelength to diffract? That's the question here. Okay. Now, no, it won't. Okay. The insufficient energy means the de Broglie wavelength would be smaller. Oh, rather bigger, too big, right? So, insufficient energy. Means large de Broglie wavelength for the electron, right? And therefore, no diffraction. So, little or no diffraction. Little or no diffraction observed. Okay, so unable to resolve nuclear rages. Okay, that's the reason here. Okay. Let's do the last one. Experiments with many nuclides suggest that this is the case. A is the number of nucleons in the surface. Show that the density is therefore the same for all nuclei. This is actually in the textbook. This particular question happens to be in the textbook. Okay.
Oh.
Yeah. I'm also surprised that I saw this here. when I first saw it. This is the exact same question in the textbook.
Can I? Which
Okay.
topic do you think I can find that in?
I'm not. Let me double check if it's still in the in the new textbook. But in the old textbook, it would be in topic. That's 8, 9, 10. Topic 12. In the old textbook.
Okay.
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 All right. But anyway, let's just do this here. Real quick. Density is equal to mass over volume, right? But mass is proportional to A, right? And then volume is proportional to R cubed, right? And we see here that our R is proportional to A raised to 1/3, right? So this means putting these two together, V is proportional to A 1/3 raised to cubed, which means V is proportional to A, right? So that means putting it back here, density is gonna be equal to some constant times A divided by some other constant C times A as well, right? So what happens? A and the two A's cancel out. We're left with a constant. K over C, which is again some constant. We'll call this some constant B. Okay? Constant. So the density of nuclei are more or less the same for everything. Okay?
Okay.
All right. Let's see. Well, heat. Last two questions we have are about heat. First one is entropy. The second one is heat engine. Okay, let's do the heat engine question now. I think we can do that. Yeah.
If you're okay with, I mean, the time is over.
I'm fine. I'm fine with it. Anyway, let's just, yeah, I think we better do this last question here. Yeah. So let's take a look at this. The heat engine, it takes energy QH from the hot reservoir. It delivers work and rejects heat energy to the cold reservoir. What's the efficiency of Y? Okay.
I got 40.
40. Okay. So what's the efficiency of a heat engine? We have that formula here, right? The efficiency is equal
Energy
to
in over.
E in
No,
over.
power over energy.
Okay. Actually, no, that would give us a time. Power over energy gives us time. Efficiency would be power out over power in, right? Okay. This is one way. Power in. This is also the same as energy out over energy in. But for, let me see if it's in the data booklet. I think it is. Thermodynamics is topic B. Is it here? Thermodynamics Q W U S entropy adiabatic process. There is one specifically for the Carnot cycle. Okay, so this particular thing, this is 1 minus the temperature of the cold reservoir over the temperature of the hot reservoir. This is for Carnot cycle. Carnot engines. Okay. Now, what do we know about engines generally? Even though it's not stated, we will assume that for DP that all of our engines, unless otherwise stated, are Carnot engines. Okay. So we can actually do this. Can we do this? Actually, no. Let's see if we can do this, but let's take a look. Let's look at the efficiency of X. Okay, that should be, what's the useful power here? The useful power here is W, right?
Yep.
Okay, and what's the useful and what's the energy in? The energy in is this QH. Okay. All right, so that's the efficiency of X. Our Y, the efficiency of Y, is going to be the same thing. We're going to take that useful power output, that's 2W, all over this thing, 5 Q. Okay. So we get these two things. Does it say anything about the efficiency of X? Okay. So okay, hold on. It's either there's something missing or there's something I missed.
It's a single question.
It's a
so,
single question, right?
there's no.
So okay, so that means I may have missed something. Hold on. Efficiency of X, efficiency of Y is that. So this is
What
gonna
does it mean?
QH, right? Sorry, say that again, please.
What does it mean to reject 7Q?
This means okay. If we draw this as a diagram, so basically this is your engine, right? Engine. Okay. So what happens is you put energy in. This is your QH. Okay. This is going in, right?
Yeah.
Okay. Then it does this. This is the work done. So this is W, right? And also, the heat engine will always, whatever goes into the heat engine has to go out of it, right? So this is gonna be the QC, and it's rejected because it's literally being ejected by the engine. Okay.
Okay.
Okay. So this is rejected, which is released by the engine, right?
Yeah.
Okay. Of course, what happens here is the smaller that QC is, the more efficient your engine is, right? Is there something else that we need to look? Oh, okay, all right. Okay. What else do we know? This goes 5Q. This is okay, let's just do this here. This rejects QC, right? I think this is the missing information that I was wondering about. This rejects 7QC, right? So the efficiency, oops, okay. So let's take a look at the efficiency of X here, or rather Y. Hold on. Takes heat 5QH to deliver. Okay. Hold on. What's just a 7QC have to do with it? Okay. All right. So we'll have to do it like this. Remember that the work done is equal to the QH minus QC, right? So that's what we have to do here. Let's just do it for the efficiency of Y, yeah? So this is going to be equal to, for Y, what do we get? 2 times, our QH is 2 QH, right? Now, here, then minus 7 QC all over 5 QH. Right. So what's going to happen here? This is going to become 4 QH minus 7 QC all over 5 QH. So we're now going to be left with 4/5 minus 7 QC over 5 QH. Okay. So this is the efficiency of Y. Okay. So okay, now let's do the same thing for X here. What are we gonna do? The efficiency here, efficiency of X will be equal to the same thing, QH minus QC all over QH. That becomes 1 minus QC over QH. Okay. We are now going to okay. So what next? Let me think now. Okay. So we have these. What's the efficiency of Y? This is already 80%. Then you're gonna subtract something as well, right? So, what was it? What was the answer? It was 40%, right?
No, I got 40. I think the answer was B.
B, 16%. Let's see why how can we get 16 with this? Uh okay.
We can even do it next time.
Okay, I think
on
we can do it
Saturday.
next time. We'll do it next time. Okay. Since I am a bit lost here, yeah, we'll do it on Saturday. I'll try to find out what this is, what the missing thing is. Okay.
All right.
All right. So we'll end it here for tonight or for today for you. So any other questions you'd like to do? Just send it over.
No,
So
it's
yeah.
okay. Yeah, you can finish it
All right.
later.
All right. So I'll see you on Saturday again, and you have a good day.
Yeah. Have a good day.
All right.
Bye
Bye
bye.
bye. Okay. So this is why I don't like thermodynamics personally. Oh. Okay, we have one comment against spam from Twitch, and we have one from yeah, we have one from YouTube. Face blue wide eyes. Okay, I wonder who this is. Thank you either way. All right, so we will finish this again, this particular lesson on. We'll finish this particular lesson on Saturday. So go. So for those who are watching the stream, yeah, you can join us again on Saturday. At this time right now, so we're gonna start on Saturday at this time wherever you are, so that's 48 hours from now. Yeah, so okay, so with that I will go through this again. I'm gonna see what I missed, and then we're gonna go through that. I will say this though, this is one of those topics, even though I've studied this several times, this still is difficult. Now, I think I'll look for that first. Hold on. Okay, let me look for that particular thing first. Okay, you may have seen this. All right. Okay, this is a real book. I'm gonna basically copy the book now. Copy the image from the book. Let's not use that. Let's use a different one. Is this it? Is this a good version? Okay, this is a good version. Let's copy this. Okay, I'll post it here on the board. I find this meme so funny, but at the same time, this describes a lot of physics students when we're doing, even when I was a student, this describes almost everybody while doing thermodynamics. Let's see. There we go. And let me zoom in. Okay. I want you to read that. I'll be on for a minute. I just want you to read that. The first paragraph. Okay, I'm just letting you read that because if I read that out loud, I don't know what's gonna happen. Okay. All right, so we'll end it here. So again, like I said, that first one, that's true. Okay, this is absolutely true. Now, why? What's with statistical mechanics? So statistical mechanics is the basis of thermodynamics. Okay. All right. So anyway, let's remove that now and let's end the stream. So with that, before you go, don't forget to like, share, subscribe to the channel. So on YouTube, Facebook, TikTok, Instagram, and when we go live, we're also on Twitch. Of course, any support would be welcome, and thank you for those who have been supporting the channel. So with that, I bid you all good morning, good day, good afternoon, good evening, good night, wherever you are in the world, and stay freaky, everyone. Bye bye now.